Welcome to part 2 of the work and energy lecture videos. So I ended off with kinetic energy in the last lecture, and this will be potential energy. So in general, potential energy is associated with forces, and they're forces called conservative forces. We don't really need to use that fancy term for this course, but they are forces where if you move things around in the vicinity where that force is acting, the work done does not depend on the path that you take from point A to point B. So things like gravity and elastic forces doesn't matter how you get from a different elevation, whether you go straight up or if you go along a long incline. Nor does it matter how you compress the spring, although you can kind of wreck a spring. Forces such as friction, well, it definitely depends how you get somewhere. So if you drag something across a really long incline, as opposed to lifting it vertically up, you're going to have to do a lot more work against friction. So that is not a conservative force. There is no such thing as the potential energy of friction. So gravitational potential energy. So this quantity we define when we're in a gravitational field, and gravitational potential energy only changes when you move vertically. So you're moving either in the direction of gravity or opposite the direction of gravity. If you move sideways across the gravitational field lines, you do not do any work. Okay, so this picture just shows you that the thing that counts is the vertical distance that you move something. So here's before, if it's low and then you have to lift it up. So this is the force you apply. Then you've done work, and up here you have more gravitational potential energy stored, and it's a type of stored energy. It's now stored in that book, or potential energy. And if you let go, you'll get it right back out again. The book will fall down, the gravity will do work, and you'll get the energy out that you put in. Now, as I said, it doesn't matter how you get from one elevation to another. So in this picture, it's showing if you start down here, which we define to be 0. Now, this definition of 0 is completely arbitrary. You make it whatever you want. I always try to choose 0 so it's as low in the picture as possible so that I don't have to deal with negative numbers. But how this person gets to this elevation of 100 meters doesn't matter. Whether they jump, or they got a jet propulsion here and they go straight up, or whether they go along an incline that's quite steep, or along a less steep incline this way, it doesn't matter. The amount of potential energy they will have stored up, having done the work against gravity to get up there, is the same. Okay, now if we're always worried about work done by gravity or by someone lifting or lowering something, so we have to keep this straight. So remember, the force of gravity is always down. That never changes, doesn't matter what you do. And so if something moves down, if the displacement is down, these two are in the same direction, this will be positive work done by gravity. Okay, so notice how they're using S over here, and they're using W for the force of gravity, but that's okay. So the fact that the angle here, theta, would be 0, because those two things are parallel to each other. And so the work, remember, it's force times distance times cosine theta. And so this is positive. Now, if it's positive work done by gravity, the potential energy actually decreases. The relationship between the work done by gravity and the change in potential energy is there's a negative in there. So we just kind of intuitively know that the higher something is, the bigger the potential energy. So up here, it's got big gravitational potential energy, and down here, it's got small. It's really the ability of something to do harm or damage to something. So the higher the rock or block is above your head, and then if it falls down, the higher it is, the more damage it'll do, the more potential energy it had to start with. Okay. Now, if you lift something up, so you're lifting something up, it doesn't matter. The force of gravity is still down. But now the displacement is up. So now gravity here is doing negative work. You're doing positive work, lifting it up, but gravity is doing negative work. And so this theta would be 180 degrees between those two. And remember, the cosine of 180 is -1. And so the work here is a negative number. And because change in potential energy is the negative of the work done by gravity, the potential energy now increases when you lift it up. Now, as I said, the zero, it doesn't matter where you put it. It's all about changes in potential energy that are related to work. So if this person on the left decides to make the ground 0, well, then she says that the rock has potential energy of, well, it's mg times y. But if this fellow decides to make his 0 here, he says potential energy 0. But it doesn't matter. If this rock moves up, they would both agree that the change would be positive. Whoops. Okay, let's do an example. Now, did we get a formula? Maybe didn't get the formula yet. Anyway, the gravitational potential energy is mgy, where y is the vertical height. So now, and then delta change in gravitational potential energy be mg delta y. Okay, so this is the symbol for gravitational potential energy. In joules, all energies are in joules. That's the mass that's being moved around in kilograms. G is 9.8 newtons per meter, strength of the gravitational field. Newtons per kilogram. And then Y is the height. And that would be in meters. Now, once again, look at these units. For U, we've got a kilogram for the mass. We've got a Newton per kilogram for G. And we've got a meter for the height. So once again, this is kilogram, because that's in the Newton. These kilograms cancel. Meters squared per second squared. Oh, man, it's making these funny marks. Okay, and so there we have it, a joule, as we saw before. Okay, so we want the work done when this 20 kilogram mass is lowered from 6 meters to 2 meters. So work by gravity is mg delta y. Has to be a change. Okay, now it's being lowered. So this is going to be a positive number or a negative number. Remember what we said. When something is lowered, the force of gravity is in the direction of the displacement. And so this is positive. And so it's the mass. What mass do we have here? 20 kilograms times 9.8. And the displacement was 4 meters. From 6 to 2, so it's 4 meters. Okay, and so this would be, work that out. Okay, 784 joules. Now, the change in potential energy, which is the negative of the work done, would be negative because it goes down. And so this would be 784 joules. I want to do this because you got to be careful about these Y initial and Y final and how you're going to do this. So let's just put this up here. If Y initial is the higher of the two heights, and Y final, because remember, you always go initial to final, so it's going down. Y final is 2. Delta Y is always defined to be final minus initial. That's what a delta means. And so this is a negative number. 2 minus 6 is negative 4. And the change in potential energy is the final minus the initial. So it's mg delta y. And so that's why this is a negative number. So this is all good. This is fine. Using delta y up here is not a great idea. I would just leave that as a d for distance. And then once again, you figure out theta and use the theta appropriately. In this case, theta is 0, and this is a positive number. Okay, that sometimes causes a bit of confusion. Okay, now we can move on to elastic potential energy. So this is associated with springs, bungee cords, any kind of elastic medium that gets stretched. Someone has to do work on it to stretch it. And once that work is done, it now has stored up as elastic potential energy in the spring or in the bungee cord or elastic. So here we have a spring, nothing is stored. It's just sitting there in equilibrium. If someone comes along and applies a force, this force will compress the spring. You will be doing work to compress the spring, and the spring now has stored up elastic potential energy. Now, it depends how much you compress the spring. This value of X is very important. Okay, and there is a law called Hooke's law that says that the force required to compress a spring is directly proportional to this amount of compression, and therefore the elastic potential energy can be defined by US. Okay, so this is elastic potential energy. This would be in joules. This K is called the spring constant. This is how springy the spring is. So if it's a very stiff spring, this will be a big number, like the springs of a trampoline could have thousands of newtons per meter are the units for the spring constant. It's how much force is required to compress at a certain distance. And then this X is the amount of compression or stretch. I mean, you can stretch a spring and also store energy. All you have to do, remember, if something has the ability to do some damage, when you let go, you have stored energy in there. So this is amount of stretch or compression in meters. Okay, so once again, here, let's look at these units. So we've got the Newton per meter for K, and then we have meters squared for X. And so that's a Newton times a meter, just like for work, force times distance. This is once again a joule. Okay, so all these formulae always work out to the same SI base units, kilogram meters squared per second squared. Okay, so let's do an example here. How far do you have to stretch a spring with a spring constant of 1500 newtons per meter to store 400 joules of energy? Okay, so we're given that the amount of energy stored is 400 joules. Given the spring constant, fairly big number, that's common. It could be like tens of thousands if it's like in a suspension system of a car or something. It could be huge. Or it could be tiny. It could be like 0.1 if you have a slinky or something like that that's not very springy. Okay, and then we want to know X. Okay, so we use the formula, the spring constant, 1/2 kx squared in there. And so X, solve for X, would be twice, multiply by 2, divide by K, and then take a square root. I really don't like how that, there's those lines in there. 2 times 400 divided by 1500 per meter. And we get that you have to compress or stretch, this one's stretch, doesn't matter which, And the answer is 0.73. 0.73 meters. So 73 centimeters, you would have to stretch that spring if you wanted to store that much potential energy. So that's part A. Now part B was, how much further do you have to stretch it to store another 400 joules of energy? Now, the answer is not twice 0.73. This is a non-linear function. So the fact that this x is squared means that the relationship between this energy and x, you did a little graph, this is a parabola. So if to go from 0 to 0.73 stored 400, well, we don't have to go twice that to go way up here to 800. So the answer is not twice 0.73. So how do we get the answer? Well, we use change. We use the change in the spring energy now has to be 400 from this 0.73 up to whatever the final length is. And any change is always defined to be the final energy, so that'd be x final squared minus the initial squared. Now we know x initial is going to be the 0.73. That's where it starts here. So that's the 0.73. And this is the unknown. So if we solve for x final, so let's just redefine this. I'm going to add the 400 plus the half k times the 0.73 squared. Then I'm going to divide by half k. And then have to take the square root of all that. Okay, and the k is the 1500. And when you do that, it turns out that x final is 1.03 meters. So it only moved over, if you take the difference. So it moved from 0.73, that was the initial, to the final 1.03. So the change was only 0.3 meters. So I only have to pull it another 0.3 meters to store up an equal amount of energy, because it's much more difficult to pull once I'm out here. So the more you stretch it, the harder it is to pull. Oh, there was an extra sheet there. Okay, so the next form of energy that we have to worry about when we're doing conservation of energy is thermal energy, heat. Basically, this is just heat. Okay, now, when we talk about heat, if we're going to have it internal to our system, then we have to include whatever surface is getting hot. And so it means that you just have to include the floor or the slide or well, the bungee cord. A bungee cord will get hot if you stretch it back and forth. So this kind of system simply has to include the interaction between the object that's sliding. It's always sliding. It's always from kinetic friction that you're going to be calculating heat. Okay, so this is the symbol they use for heat. Delta E thermal. I just use the word heat. Now this is a positive number. This is just heat. The force of friction. So that is the force of friction, the magnitude of the force of friction. Force of friction. And then this is the distance over which the object is being dragged. And this would be in meters. And this, of course, is in newtons. And so heat, once again, is a form of energy. So it's joules, newtons times meters. Okay, so, and that's a positive number. This is always a positive number. You can't have negative heat. And so when they use delta E therm, I would just call it heat, but this is a positive number. This is positive. Okay, now, not to be confused with the work done by friction. If you're calculating that separately, that's a different kind of quantity that if you're asked to calculate that, that would be a negative number. So because friction always points in the opposite direction to the displacement when it's kinetic friction, then the angle is 180 and the work done by friction is a negative number. But this quantity, the way they use it here, this is a positive number. Okay, so And this work, that's not work done by friction. That'd be something else. That'd be like an external force pulling or doing something. And these things will be inside your system. So like gravity obviously is going up and down, and heat or elastic or something. Okay, so let's just see how much heat is generated when you drag a box. So this is delta E therm they're asking for, or just heat is, and I'm going to put absolute value to make it really clear, force of friction times displacement. You could use a D if you wanted to. Okay, so coefficient of kinetic friction, do you remember? So this is Fk, this is mu Fn times delta X. And if it's on a horizontal, just a floor, I mean, floors are always horizontal, the normal force would be mg. Okay, so we basically just multiply all these numbers together. 0.3 times 10 kilograms times 9.8 per kilogram times 5 meters. And this would be heat. Multiply all those together and you get 147 joules. Okay, positive number. And let's just make a note here. Note work done by friction. So this would be if this was now internal, or sorry, external to your system, and you didn't care about the floor really. You're just worried about how much work friction does. So work done by friction is a negative number. Because when something moves this way, the displacement is that way. Force of friction is this way. We don't care about the floor. We're just worried about the box with this force on it. And theta is 180 degrees. And so cos theta is -1. It's trying to slow it down. Remember, anything trying to slow something down does negative work. Okay, so here's an example. We're going to calculate the work done by all these forces and the package's final speed. Okay, so it's sliding down this incline. There's friction. And so we need to calculate the work done by every force acting, and then the net work. And remember, then use the work energy theorem. Net work is changing kinetic energy. Okay, so let's get a little picture here. We'll do this incline. Now it's a funny way that they've talked about they say it dips down 53 degrees from the horizontal, but what they mean is it inclines up at 53 degrees above the horizontal as well. Okay, and then it's a box on here. Now the distance it travels is important because that's the direction. This they say is 2 meters. That's the displacement. So it's along the incline and it's 2 meters. Okay, now we need this height because this height is going to be the work done by gravity is determined only by the change in vertical distance here. So we're going to call this y. As you can see from that triangle, that y is equal to 2 meters times the sine of 53 degrees. And so the distance vertically that this thing moves is 1.6 meters. We need that. Okay, so let's get the forces on this thing. What are the forces? Well, we've got the force of gravity. We've got the normal force. And we've got the force of friction. That's it. Those are the only forces. Okay, now as this thing moves down the incline, this does no work because it's perpendicular to the displacement. So this does no work. Okay. Now, gravity. The thing is moving vertically down. This is going to do positive work because it's in the direction. And it doesn't matter what path it takes, doesn't matter that it's on an incline. It's just how much vertically down it moves that counts. This, the angle is 180 to the displacement. And so this does negative work. And it depends on the length of the path. Okay, so for gravity, I don't know, do I have an extra slide? I do. Okay, so the work by gravity it's positive. It's the force of gravity times the distance vertically down. And so this is mg times the 1.6 meters. Okay, so that's the mass is 8 kilograms times g times 1.6 meters, and gravity will be doing positive 125 joules of work. Okay, friction is the force of friction times that same displacement, but it's a negative number, cosine of 180. So this is negative mu Fn times d, because force of friction is mu Fn and d is the distance along the incline. Whereas here I'm going to use the 2 meters. Okay, so remember what the normal force is on an incline? It's the in-slope component of gravity, so it's mg cosine theta. Now this theta is not the 180, this is the theta of the incline, that would be 53 degrees. And then times d, so this would be negative 0.4 was the coefficient of friction, 8 kilograms, g cosine of 53, and then the distance along which the thing is dragged, 2 meters. So this turns out to negative 37.7. Okay, so the net work, you just add these together. It'll be 125 minus 37.7. And this comes out to 87.3 joules. Okay, that's the net work by all forces. That's what's related to the change in kinetic energy. So kinetic energy, work energy theorem is W net is delta K, 1/2 mv final squared, 1/2 mv initial squared. So this would be 1/2 of 8 kilograms times v final squared. Oops, no more slides. Okay, so let's just, we've got this W net, here it is, 87.3, and we can work out VF. Turns out to be 4.67 meters per second. Now, had there not been any friction, this is the answer. It would have been going faster because it wouldn't have lost, this is the amount of energy essentially that's losing to heat. And so the final velocity is smaller than if there were no friction. Okay, so we'll end it there.